Good morning, all of you. I am in this session. I am going to discuss that is module 4. That is you can call it the refrigeration system. Okay. Before going to the different refrigeration system, you should know the definition of refrigeration. Refrigeration is defined as the art of producing and maintaining, say, temperature lower than the atmospheric temperature. Refrigeration is defined as is the art of producing and maintaining a lowest temperature when it will be compared with the atmospheric temperature, where we have to produce a cooling effect. In that area we have to maintain a temperature below the atmospheric temperature, that is you can call as a refrigeration system. Okay, that always the refrigeration system we are discussed about in terms of tons of refrigeration. The 1 ton of refrigeration is equal to 210 kilojoules per minute. What is meant by the ton of refrigeration system? Always the refrigeration system we have to discuss in terms of tons of refrigeration. 1 ton of refrigeration is equal to 210 kilojoules per minute. What is meant by this 1 ton? That means a 1 ton of refrigeration is defined as a quantity of heat is removed, a quantity of heat to be removed in order to get 1 ton of ice, in order to get 1 ton of ice in 24 hours, when the initial temperature of water is 0 degrees centigrade. That is you can call it 1 ton of refrigeration. The 1 ton of refrigeration is defined as a quantity of heat to be removed in order to get 1 ton, in order to get in order to get in terms of 1 ton of ice in 24 hours, when the initial temperature of water is 0 degree centigrade. That is you can call a 1 ton of refrigeration system. 1 ton of refrigeration is equal to 210 kilojoules per minute. Okay, now before going to the refrigeration cycle, we are having a two systems is there. That is a one is what? Refrigeration system. Another one is what? Heat pump. The refrigeration system, it will be operating with any these systems, which will be the operated by the second law of thermodynamics. Any system is there, that means any system should operate means minimum two energy barriers are required. That is one is higher energy barrier, another one is lower energy barrier. So that's why we are taken into account here. First one is refrigeration system. Here in the refrigeration system, the above that area, that is you can call it a source, that below that area you can call it a sink. Okay, now where we have to get a cooling effect here in the refrigeration system, there we have to absorbing a heat, that is a T2 temperature is there. From the T2 temperature we can absorb heat, heat the amount is Q2. Then that Q2 amount, then we are supplying work to the system. Then we are Q1 amount of heat to supply to the source in such a way that the work which will be executed here. Okay, that means that heat never flow from lower energy level to the higher energy level. Always we have to supply a work, then only the heat flow from lower energy barrier to the higher energy barrier. Okay, similar way that the system should be working here also. Then here the refrigeration system, that means we have to produce a cooling effect here in the lower region. So that's why where we have to produce a cooling effect, there we have to absorbing a heat. How much amount of heat will be absorbing in such a way that it will be produces a cooling effect. This is a simple mechanism which will be existing throughout the chapter, throughout the session. We are to discussing the same thing here, where we have to get the cooling effect, there we have to absorbing a heat, then how much amount of absorbing it in such a way that that produces a cooling effect. Here this is you can call it the refrigeration system. The COP of refrigeration system is equal to, that is a Q1 is the major amount, that is a Q2 is the major, Q2 divided by W. Then similar way it will be having another one system is there, that is you can call it a heat pump. That heat pump is also working between the same two energy barriers, then only that the system should work. That is based on the second law of thermodynamics. Heat pump is there here, that is a source T2, and sink is T1 is there. We have to lift the source to the sink. Here we are supplying work here. Okay, from lower to the higher level we have to lift it, so that means work which will be required. This is COP of heat pump. COP of HP is equal to Q1 divided by W, which will be existing here. Okay, this is the simple mechanism which will systems should be know, that refrigeration system and heat pump. Then we'll be move on to the different types of refrigeration system. That is a Carnot refrigeration cycle, air refrigeration cycle, vapor compression refrigeration system, vapor absorption refrigeration system, steam jet refrigeration system. Okay, here the five refrigeration system which will be existing in our syllabus. We have to discuss these five things only. Okay, now first we have to discuss about Carnot refrigeration system. Okay, already we know the Carnot refrigeration cycle is a ideal cycle. It will always, it will be containing four different process. Two process are isothermal process, two process are adiabatic compression and expansion. Adiabatic compression and expansion process, isothermal compression and expansion process. Okay, already we know this Carnot cycle. That reversible Carnot cycle, it will be acts as a heat pump and also a refrigeration system. Here also the same thing which will be existing here also, that Carnot refrigeration cycle. This is what the PV diagram, this is what TS diagram. Okay, that is a one, this is the point one is there, that is the expansion process, isothermal expansion process, isothermal expansion process. In this isothermal expansion process, heat absorption will be taken place in the lower region. This is you can call the TL, this is you can call the TH, higher region 1 to 2, isothermal expansion process. Okay, now that is a process 2 to 3, adiabatic compression process, adiabatic compression process. Then 3 to 4, isothermal compression process. In the isothermal compression process, heat will be liberated to the atmosphere, heat will be rejected to the atmosphere. Then 4 to 1, once again, that is a adiabatic expansion process, 4 to 1 adiabatic expansion process. Like that the system should work here. Then what is the COP? The generalized definition of COP is equal to refrigeration effect divided by work supplied. COP, this is generalized definition. COP means what? Refrigeration effect divided by work supplied. Okay, COP of Carnot cycle is equal to, that is what, Q, it will be absorbing here, that is what, Q1 divided by Q2 minus Q1. That is what, Q2 here heat will be rejected, Q1 is absorbing from the lower region, it becomes Q1 is a very important criteria. That is what, Q1 divided by Q2 minus Q1. This is the COP of Carnot cycle. Okay, very simple expression is there here. Okay, now another one cycle, that cycle you can call the air refrigeration system, is also called the bell column cycle. Air refrigeration cycle and bell column cycle. Okay, here that black diagram which will be existing like this. Here that is a compressor is there, that is a 1 to 2 isentropic compression process, 1 to 2, that is what, isentropic compression process. 2 to 3, that is what, uh, uh, 2 to 3, that is a heat exchanger should be taken place, constant pressure, that heat that is a cooling of air which will be taken place. Then 3 to 4, once again, that is the expansion process. Okay, here the pressure which will be reduces, reducing the pressure and reducing the temperature, once again pass it to the refrigeration system. Here the heat absorption will taken place, which will be produces a cooling effect. This is the way of working principle behind air reference system, is also called a bell column cycle. Okay, 1 to 2, that is a isentropic compression process. 2 to 3, here cooling of air which will be taken place here in the during the heat exchanger. Okay, here in the cooling of air will be taken place here, the heat rejection will be taken place to the atmosphere. Then it will be cooled air and high pressured air which will once again pass it to the, in the process 3 to 4. In the process 3 to 4, here the expander is there, the pressure which will also reduces, a low pressure low temperature air once again pass it to the here refrigeration system. Here the absorption of heat will be taken place here, such a way that it will be produces a cooling effect here. This is what that working principle behind bell column cycle, bell column cycle. Okay, next, that is what we have to calculate, that COP of the cycle, net refrigeration effect divided by work supplied. Okay, here the work supplied will be taken place here, WC. WC is equal to CP into T2 minus T1. Okay, expander work is there here, WE, the expander, CP into T3 minus T4. Then we have to net work done is equal to WC minus WE, that is what, CP into T2 minus T1, minus Cp into T3 minus T4. It should be clubbed it. Then you should write down here COP is equal to Cp into T1 minus T4. That is what refrigeration effect. Cp into T2 minus T1 minus Cp into T3 minus T4. It then here T3 from the intercooling. For a perfect intercooling, here what happens here, T3 is also equal to the T1 in such a way that the heat rejection process will be taken place here. Then here what happens here, T1 minus T4 divided by T2 minus T1 minus T1 minus T3. Instead of T3 I can write down here T1 here T1 minus T4. Here I will denominator it will be cancelled here, 1 divided by T2 minus T1 divided by here T1 minus T4 minus 1. Okay, in the denominator you can take a common term of T2 here, 1 minus T1 divided by T2 here. Here T1 you can take a common term here in the denominator, 1 minus T4 divided by T1 minus 1 here. Then go to the process, isentropic compression and expansion process. Based on this process here, compression process, T2 divided by T1 is equal to P2 divided by P1 to the power of gamma minus 1 divided by gamma. Then T3 divided by T4 is equal to P3 divided by P4 to the power of gamma minus 1 here. Then P2 is equal to P3 based on this PV diagram here. That is what P2 is equal to P3, P4 is equal to P1. Then I will write down here the RHS sides are equal. Then I will interchange the terms here. T2 divided by T1 is equal to T3 divided by T4. Then I will interchange the term here. T4 divided by T1 is equal to T3 divided by T2. Then T4 divided by T1 is equal to T3. Instead of T3 I can write down here T1 divided by T2. Then expression is become COP is equal to T1 divided by T2 minus T1. This is what the COP of air refrigeration system. This is COP of bell column cycle. This is COP of bell column cycle. It is very simple expression is there here. You can once again practice it, you can get the things here. Okay, and advantages of air refrigeration system. The air refrigeration system, the air, we are using a working medium, so it will be abundantly and cheaply available this refrigerant. Okay, there is no dangerous and toxic effects to leakage of air. The total weight of the system per ton of refrigeration capacity is very less, and also it will be this bell column cycle, it will be having a disadvantages is there. What are those disadvantages? The quantity of air required per ton of refrigeration capacity is far greater than the system of refrigeration system. They greater than other system of refrigeration. The quantity of air used will be more. The COP is low and hence running cost is high. The quantity of air which will be more when it will be compared to the other refrigerant system. First one, the COP is very low. Okay, these are the major disadvantages of bell column cycle. Okay, then another one, refrigeration system. That refrigeration system we can call the vapor compression refrigeration system. Okay, now in the vapor compression refrigeration system here, 1 to 2 the isentropic compression will be taken place here. That starting point 1 is there, stage at 1, that is a low pressure refrigerant, a dry saturated refrigerant. It will be passed to the compressor. Here in the compressor, high pressured liquid refrigerant once again passed to the condenser. Here the condensation process will be taken place. It becomes liquid refrigerant, high pressure refrigerant. It will be passed to the throttle valve. Here in the throttle valve, that is a liquid refrigerant and low pressure, low temperature. That refrigerant once again passed to the refrigerant system. Here in the refrigeration system, we have to produce a cooling effect. That means we can absorbing a heat from this system, which will be produces a cooling effect. This is what the vapor compression refrigeration system here. That is a stage 1. The stage 1, it will be dry refrigerant, saturated refrigerant, it will be low pressure refrigerant. Here it will be the compression will be taken place here. At stage 2, high pressure refrigerant once again passed to the liquid refrigerant, passed to the condenser. That cooled liquid refrigerant and high pressure refrigerant once again passed to the throttle valve. During the throttle valve, that the pressure is also reduces. That low pressure, low temperature liquid refrigerant, it will pass it to the refrigeration system. Here the absorption of heat will be taken place, which will be produces a cooling effect here. This is the working principle behind this vapor compression refrigeration system. 1 to 2, then that is what compression process. 2 to 3, constant pressure. Okay, 2 to 3, constant pressure, it will be remains constant. The heat rejection process will be taken place. 3 to 4, once again the pressure it will be reduces, the expansion process. 4 to 1, that heat absorption will be taken place here. This is what TS and pH diagram. This is why we are written is pH diagram here. The phase change will be occurring. So that's why I'm representing here. This is a saturated curve here, saturated curve. This line it will be getting as a saturated liquid, as a saturated water line points. Okay, this side, that the right side curve, it will be representing for saturated vapor, saturated dry, saturated steam. Okay, and that is a condition. You should remember it, all these things. Vapor compression refrigeration system. Okay, now this is what's the superheating of steam which will be existing here. Here we are having a different case studies is there in this vapor compression refrigeration system. Before going to those case studies, first we should know the simple expression is there here. The COP of vapor compression reference system, heat extracted at low temperature divided by work supplied. That is what refrigeration effect divided by work supplied. That is what Q is equal to H1 minus H4. This is you can call the refrigeration effect. Work supplied, that is what H2 minus H1, that COP become H1 minus H4 divided by the refrigeration effect divided by work supply, that is what H2 minus H1. Then H1 minus H4 becomes fluid, saturated water, that is what H2 minus H1. Or at stage 4 it becomes saturated liquid, then only the heat absorption will be taken place here at force. Liquid, low pressure, low temperature, that is a liquid refrigerant, then only the absorption of it will be taken place in the refrigeration system. So that's why it becomes saturated liquid, saturated water, that is it becomes HF4. You can call it the HF4. This is what the simple COP expression for vapor compression refrigeration system. Okay, this vapor compression refrigeration system, it will be having a some few case studies is there. Okay, what happens, those what are the different case studies we are discussed one by one now here. Okay, these case studies we are using while solving the problem. We have to write down these case studies, how to write the TS and PV and HS diagrams and all. We should know the these concepts and all, how to write the things here. Okay, one by one we have to discussing of these case studies of vapor compression refrigeration system. Just you can wait. I will show it to you. These are the case studies here. Okay, one by one I will discuss it and how to write the TS and pH diagram. The first one, theoretical vapor compression refrigeration with dry saturated vapor after compression. After compression process 1 to 2, it becomes dry saturated. That means it will be touches the, it will be 0.2, it will be exactly at the curve. 1 to 2, that is isentropic compression, it should be exactly at the 0.2, that is you can call it a dry saturated. This is very important. Then 2 to 3, that is what 2 to 3 is what heat rejection process, constant pressure heat rejection process, isothermal process, heat rejection process. Okay, then 3 to 4, once again expansion. 4 to 1, it will be existing here. Okay, this is very important here. At dry saturated, after compression it becomes dry saturated. Dry saturated means at 0.2, it should be exactly at the curve, on the curve. Then COP is equal to refrigeration effect. Here heat absorption of the lower region, H1 minus H4 divided by H2 minus H1. Then H4 it becomes is also equal to the HF3. HF3, that is saturated liquid, H1 minus HF3 divided by H2 minus H1. Okay, this is very one case study. After a dry saturated means it exactly at the 0.2, it should be exactly at the curve. Okay. Then next one, theoretical vapor compression refrigeration with wet vapor after compression. After compression process, that 0.2 within that curve, not exactly at the curve. Exactly at the curve means dry saturated. Wet means within that curve which will be existing here, 1 to 2. So that like that only you should write down when the problem which will be asking the problem with wet after compression of that it becomes wet, then we have to write down the TS diagram. It should be exactly, it should be like this. Here also just you can observe here in the pH diagram 1 to 2, it becomes wet condition. After compression, the refrigerant becomes wet. That means within that curve, then only you should write down this. In this case studies, we have to write down the pH and TS diagram. Don't touch us this curve here, the point 2. Within that curve, you should write down. Then COP is equal to H1 minus HF3 divided by H2 minus H1. Then another third one, theoretical vapor compression refrigerant with superheated vapor after compression. Okay, when this point 1 to 2, it becomes superheated. Beyond this curve we should write down here, beyond this curve, the saturated curve, then it becomes superheated steam, superheated vapor 1 to 2, like that only you should write on. Then 2 to 2 dash, 3 4, 3 to 4, and 4 to 1. Here also 1 to 2, 2 dash, 3 and 4. Beyond this curve, that point 2, it will be existing, that is a superheated vapor region. Then COP is equal to H1 minus HF3 divided by H2 minus H1. When superheated means beyond this curve, we should write down that point 2. This is what you should remember it, how to write the TS and pH diagram. We are solving one by one all the case studies. We will be having a problems is there. Then afterwards, another one case study, theoretical vapor compression refrigeration with superheated vapor before compression. Okay, before compression already that refrigerant is superheated. Then that 1 dash is there, it becomes 1 year. It is beyond the curve. Already it should be, that stage it should be superheated. Then 1 to 2, it become superheated vapor. Like that only you should write down here. 1 dash to 1, 2 dash to 2. It becomes, so before that refrigerant cycle, before compression, it should become a superheated. Then that beyond the 1, it becomes beyond this curve. 1, it becomes beyond this curve. 1, 2, 2 dash, 3, 3 to 4, and 4 to 1 dash. Then 1 is there here. This 1 is beyond, before going to the compression. Already that refrigerant is superheated. Then you should write down this type of sketch. The COP, it becomes H1 minus HF3 divided by H2 minus H1. Then the last one is theoretical vapor compression with undercooling or subcooling. Okay, then it becomes 1 to 2, that is a dry saturated condition, the liquid refrigerant. Then it becomes superheated vapor. Then 2 dash to 3 here, then it should be undercooling, subcooling. 3, it will be existing here, that is a saturated liquid, saturated vapor, saturated water at point 3. Then once again, that is a subcooling here, that is what, 3 dash, 3 to 4, it will be existing here. Subcooling, cooled, that liquid, once again the temperature will be reduces here, liquid temperature, the water temperature will be reduces, saturated liquid temperature, it will be reduces, that it becomes 3 dash to 4 dash, such a way that produces here. Here also the 1 to 2 dash superheated vapor, then 2 dash to 3, it becomes a saturated liquid. Then it becomes subcooling, once again cooling this saturated water, either liquid, it becomes 3 dash to 4. Then 3 to 4, which will be existing here also, the curve which will be existing 3 to 4. Then 3 dash to 4, 4 dash which will be existing, this another one, subcooling. Once again the saturated liquid, either water, that cooling which will be taken place. This is the way of writing the TS and pH diagram. Okay, the COP is equal to H1 minus HF3 divided by H2 minus H1. This is what the case studies of different uh, vapor compression refrigeration system. All the case studies we are having a problems is there. Okay, one by one we are discussed later. Okay, I will stop it here. Okay, the next class will be another one, two refrigeration cycle is there, that is vapor absorption and steam jet. Then I will complete this theory aspects of module 4. Okay, thank you one and all.